All right, so here's another 2 hours for me to talk. Beauty. So, there's a quiz. Who's done it?
Yeah.
I must have stuffed something up because most of you have got one of the questions wrong. I will have to look and see what I did wrong. I can't believe that you've all got it wrong.
Which page is it?
3. I think it was 3.
Which one was that?
Was it the one about the one query by any chance?
Yeah, could have been. Yeah, that's right. I think it was, yeah. So I suspect you all said equals 19010101 was a one query. Is that what you're all saying? Don't know. I can always have a look anyway, but that is not a one query because there may be multiple people with that birthday. Not that there will be any. All right, assignment 2. Having just had so much fun with assignment 1, once I work out what I want to do in assignment 2, I'll give you an assignment. Maybe it'll be rewrite the query optimizer for Postgres. That'd be fun, wouldn't it? It won't be that though. All right, so today I want to talk about some more weirdo ways of making multi-dimensional selection go faster, and then say a little bit about similarity matching, and then get on to join processing methods. All right, here's another nerd. 25 bonus marks for anyone who can tell me who this is. Wow, that would have prompted a response. Going, gone. Too late. It's Masaru Kitsuragawa. Is there anyone who's Japanese in the audience who can correct my pronunciation? I thought that was a reasonable effort. What did he do? This was an interesting fad that happened in the 90s. People trying to build specialised machines for doing stuff like databases and logic programming and things like that. Of course, they all died. Economies of scale didn't work that well anyway to justify having the specialised hardware. But one thing he did do, which is kind of relevant, maybe I'll get onto it today, is he developed a new join algorithm. So that's one of the ones we're going to talk about. For that, and I guess all his other work, he got an Innovations Award in 2009. So at least, he did that in the 90s. People looked to see how much impact it had. The actual database machine had pretty much zero impact, but the algorithm was relatively important. So he's an interesting guy and seems to have moved to quite a high position in Japan. All right. So we've looked at hashing, which is basically a way of placing records in the file so that you can find them again more easily. So that's all about placement. Indexes, where you've got some auxiliary data structure which allows you to relatively efficiently get to the records with the corresponding key values. Here's an idea where we give up the idea of order 1, which is what hashing is supposed to deliver, but generally doesn't, and order log whatever when you're using some kind of tree structure. And go back to, let's just do a linear scan, but do it on something that's much more than scanning through the tuples, okay? So we have a collection of data where each piece of data or signature is a representation of the tuple. Now, it's obviously for this whole thing to be at all useful, the signature has to be much smaller than the tuple, so you can pack lots of signatures into a page, so you don't have to read as many pages, and at the end of the process of reading the signatures, you get a relatively small number of data pages that you have to go and read. So one issue is that if you make it smaller, you're losing information and potentially you think you've got a match, but you actually don't. So the notion of false matches comes into play here. I mean, to some extent, it's not. Well, it's a little bit true that if you're using hashing, that tells you to go to a particular bucket. There may be no tuples in the bucket that actually match the query. So, you know, the hash has said go here, nothing there. So in some sense, that's a false match as well. But it becomes a little bit more prominent in this context. So this signature should use information. It can use something like a hash value for each of the attributes, put them together. Last time we were talking about putting hash values together using a, what was it called? Doesn't matter. Anyway, overlaying all of these hash values. Come on, someone tell me, what did I talk about last time? Multi-attribute linear hashing. Not called the code word. Anyway, you ended up with a hash value that took bits from all of the different attributes. So here, similarly, we're taking hash values for the attributes and we're combining them in some way to produce a signature, sticking that in a file which is parallel to the main data file. So basically we get a scenario like this, that we've got, and these are not page indexes, they're tuple indexes. So we've got all of the tuples and we've got all of the signatures, and they're basically parallel. If we've got a particular tuple slot in the file that's not in use, then the corresponding signature slot is 0. And basically, we don't care whether records are placed under this scheme as long as this signature corresponds to that tuple. Right? So we could use some other indexing alongside this. You could even use hashing for that matter. Alright, so clearly the way we're going to solve the problem here is we're going to scan through this file and say, is this a match, or is this likely to be a match? Is this likely to be a match? Is this likely to be a match? And so on, and that'll give us a collection of tuple IDs for potentially matching tuples. We'll work out what pages they correspond to, and then we'll go and read the corresponding pages. Okay, so that's the plan. So how do we form these signatures? Well, basically we take hash values for each of the attributes and we combine them in some way. Two possibilities. One is to concatenate them. So we get the hash value for each attribute. That gives us some bits, then we get some more bits, then we get some more bits, then we get some more bits. Doing that, we're likely to end up with quite a long signature, which is bad because we want these signatures to be relatively compact because we have to read them all. And the other possibility is just to overlay them. Now if you do that, of course you start to set bits. Remember, all these signatures are just bit strings. You start to set bits that you didn't really want to set, or that you set bits that could be interpreted in two different ways. So either way, you've got issues. Concatenation makes the signatures longer and therefore costs more to read them. Overlaying them makes them shorter, but you're more likely to end up with false matches. So that's the trade-off. So anyway, how do we build a signature? Well, basically we're going to use the overlay approach. So for each attribute we form a bit string which is n bits long, and k of the bits are set to 1, and in theory k is much more than m, so maybe we've got 128 bits for each tuple, and if we've got 4 attributes, then maybe each attribute has 8 bits set, something like that, maybe more actually. But anyway, that 8 bits out of 128 gives you a wide range of expressible values, if you like. So you can distinguish all the different values for the attribute. in that. So we form a code word for each attribute, and then we overlay all those code words, and basically what that means is we OR them all together. How do we generate a code word? Well, this is one way you can do it. You've got an attribute value, we'll just treat it as a string. We want k bits out of n bits. So we get a hash value, stick it into a random number generator, or we could actually use that hash value direct if we really wanted to. And basically we run through until we've got k bits set in the code word. So, and of course we just do that, every time we set a new bit, we increment the counter for the number of bits. So after we've done this, we've got a code word that's n bits long, and it's got k1 bits and n minus k0 bits. And you do that for each attribute, and then OR them all together as we see here. Okay, so generate a code word for attribute AI, and then OR it in with the overall signature for the record, and the signature starts out at 0. So that'll give us a signature for the tuple, or I've called it as a descriptor here. And here's an example. So superimposed code words is what that stands for. So this is a banking example that I've used maybe once or twice. So each of these attribute values produces 2 bits out of 12 set to 1. So the Perry Ridge value gives us that code word, 102 gives us that code word, Hayes gives us that, and 400 gives us that, and then we OR them all together to give us this tuple signature down the bottom. Okay, so you can see that sometimes we get the same bit set in 2 code words, doesn't matter, it still ends up as a 1 in the final code word. The more critical thing is that maybe we had a 1 here, and we get the 1 from here, and we end up with a 1, even though we've also got a 1 there, and potentially that can OR, even having 1 here and 1 here. And then we set 2 bits, and if we're searching for Perry Ridge, we're going to find this tuple's fine because it's also got Perry Ridge. But if it adds well, let's say we're searching for some other branch, and we also happen to have a 400 for that branch, then it would look like a Perry Ridge tuple. So let's have a look at how we answer queries, and that will become clearer. Okay, first thing we need to do, generate a query descriptor, and we do that by taking all of the known attributes. So this is kind of a little bit like what we had with the multi-attribute hashing, but different. So we've got a value for that. The others we don't know, so we leave them all as 0, and that gives us a query descriptor. Now, one thing we know, that if there are any tuples with Perry Ridge in the database, they're going to have those 2 bits set to 1. So if we can find tuples that satisfy that property, they're potential matches. The problem is that these 2 1 bits might have been set for other reasons, not related to the fact that it's a Perry Ridge tuple. So in any case, how we answer queries, basically, like all of the other schemes that we looked at, the first thing we want to do is we want to use our indexing mechanism or our selection mechanism to produce a set of pages, potentially interesting pages that may contain tuples that satisfy the query. And I should have said this is only going to work for partial match retrieval type queries, because we got no idea about ordering. So we scan through the entire signature file, and we see whether each signature matches the query. And it turns out that the matching process, or the matching mechanism, is very efficient. All we have to do is check that the query descriptor contains a subset of the bits in the signature for that tuple. And if that's true, and we can easily work that out using an expression like this, and that can be done relatively efficiently. Then we know we've got a match. Then what we've got to do is work out which page that tuple's on, grab that page ID and then add it to our list of pages to check. Right? So at the end of this, having scanned all the signatures and tested each one to see whether it matched the query or whether the query matched the signature, depending on which way you want to look at it, we then got a bunch of pages to check. We then scan through each of those pages in turn, and hopefully the set of pages that we get here is much smaller than the total number of pages in the data file. So we get individual pages, and then we've still got to scan the page to check for tuples that actually match what we were searching for. So even though we're doing a linear scan of the signature file, A, the signatures can be relatively small, and B, the test for whether we've got a match is relatively efficient. So hopefully we can do that process reasonably quickly. So here's the example. We've got, these are all of the tuples in the database. We can see what bits they've got set. We can see the bits that are said in the query descriptor. And so all we've got to do is find a tuple that has a 1 in both of those positions. So there's an example. If it's got 1s in other positions, who cares? Doesn't matter. As long as it's got 1 in these two positions, because we know that's an indication that there might be the value peri-ridge. Now in the first such tuple, that's true. In the second such tuple, it turns out that these 1 bits have been set by some combination of the code words of these attribute values, which are completely unrelated to peri-ridge. So what the query, the first step of the query evaluation is going to tell us this is a potential match and this is a potential match. If they happen to be in the same page, that's nice. We just got to read one page and then we can check whether each tuple in that page is an actual match. But if they're in different pages, we end up reading 2 pages, which is not so good. In any case, the scenario where you've got bits set that match the query signature, but not because the tuple actually matches the query, that's called a false match. So we've got one genuine match, which is that tuple there, and one false match, which is that tuple there. That looks pretty bad because we've only got 6 tuples, and a false match rate like that is not great. But one thing is that these signatures are pretty small. Okay. So typically we'd make them larger than whatever I've got there. It looks like about 12 bits or something. Right, so we're certainly interested in the likelihood of a false match occurring. So we can discuss that. Now, the way we saw it before, the likelihood of a false match seemed to be about a half. That's not great. How do we make the likelihood of a false match happening less? So one way potentially is to use a different hash function for each attribute. Basically all that's going to do, and I'm not sure how well that actually works, but I was thinking that if we happen to have a scenario where we've got numbers in 2 of the attributes and we happen to have the same numbers in the 2 attributes, we don't want to end up with the same hash value. We'd rather distinguish the fact that it's the value 100 in attribute 4 from the fact that it's value 100 in attribute 2, for example. Anyway, that might help a little bit. Obviously making the descriptors, making the signatures bigger is going to help because it gives us more range of possible values, so we're less likely to have the kind of collisions. And the other thing that's going to help is to choose a value of k, the number of bits for each attribute, such that we end up with around half the bit set. Now, of course, we don't necessarily have to have k the same for each attribute. If we've got an attribute that's only got 3 possible values, then we could have a small, or 4 possible values. We could have 2 bits for k, and in fact, in that scenario, we mightn't even want to overlay them. We might want to separate, might want to have a concatenation of part of the signature for all of the attributes except the one that has the small number of bits, and do them separately. Right, of course, the downside of doing this to make less false matches is we've got to read more data when we scan through the signatures. And if we got k too high, then we got more overlapping, so we end up with more false matches anyway. If we have k too low, then if we only set 1 bit in the code word, and the code word is 32 bits long, there's really only 32 distinct values that we're dealing with there. If we've got 100,000 different attribute values, then that's pretty bad. We're mapping them all into 32. At least if we've got 2, then we multiply the number of possible code words that we can generate. So there's a bit of a trade-off here, and it turns out that if you do all the analysis, which I'm not going to do here, you can work out an optimal value for m and k given a particular false match probability. So basically you say, what kind of likelihood of false matches am I willing to tolerate? Let's say no more than 1 in 10,000. That gives you a false match probability, and then you can use that to work out appropriate values for m and k. Okay. Oh, and the number of attributes also comes into play here. So, what kind of query costs are we going to end up with by doing things this way? Alright, well clearly we have to read all of the signatures, and then we have to read the pages that potentially contain matching tuples as indicated by reading the signatures. So how many pages of signature data do we have to read? Well, that depends on how many signatures you can pack into a page, which is CD, and there are that many signatures, so that's the total number of signature pages. How big is, or how many signatures can you fit in a page? Well, that depends on the number of bits in each signature. So we work out the number of bytes, and we work out the number of bytes in a page, and that will give us the number of signatures that we can stack into each page. So if we got a scenario like this, where we got 64-bit signatures, that's not huge, that's just two 32-bit words. The pages are that big, we got that many tuples, then we end up with something like this. So we can fit 1,000 signatures per page, and the number of pages of signatures is only 10. Right? So that's a lot better than reading. I'd need to know how big each record was. Imagine we can fit 20 records per page, because they're relatively large records, then we're going to have a lot of pages. Okay, so reading 10 signature pages is better than reading all of the data pages containing the records. Now, scanning through the signatures is going to suggest a bunch of pages to look at. Some of them are going to contain matching tuples. Some of those pages aren't going to contain matching tuples. So the number of false matches that we could expect is obviously going to be related to the false match probability, and this is all averaging out kind of thing. So total number of tuples minus the real number of matching tuples, then multiply by the false match probability, and that's the likely number of false match tuples that we're going to end up with. And that's going to be roughly like that. So if we've got a false match probability of 1 in 10,000, then 1/10,000th the number of actual tuples is likely to be the number of false matches, which not too bad. Alright, so in the worst case is every false matching tuple is on a different page and doesn't contain a matching tuple. Doesn't contain any matching tuples. So these are the number of records that do match plus the number of records that don't match. And in the other aspect of the worst case scenario is that we have one suggested tuple on each page. So for every possible true matching tuple, they happen to all be on different pages. Every false matching tuple also happens to be on different pages, and the set of those two sets of pages is disjoint. So that's the worst thing that can happen. So if there really are 100 matching tuples, they're on 100 different pages, and if there are 10 false matches, they're all on different pages. So we've got 110 pages that we have to read after having read all of the signatures. The best case scenario is that we don't get any false matches, and having read all of the signatures, it indicates a single page containing matching tuples, and we go and have a look at that and get all the matches. And the average case is where you've got some matching tuples on some pages, and maybe there are false matching tuples on those pages as well, and you've got other pages that have no matching tuples. So how much is it going? So is this going to look even plausible as a strategy? Alright, so imagine we've got pages that are that big, which happens to be the size of pages in Postgres. Let's say our tuple descriptors are that big. Let's say that's how many records we've got, conveniently chosen so that we end up with 1,024 pages, and the false match probability is like that. The actual number of matching tuples is 1,000, and they're scattered across 100 pages. Okay, so roughly on average 10 matching tuples per page that contains matching tuples. So most of the time we get lucky and the false matches happen to occur on pages that have true matches, so we would have needed to read those pages anyway, so the false matches aren't causing us any extra cost. On the other hand, 10% of the false matches occur on a page by themselves which contains no matching tuples. So that's a page that we have to read to check, and it turns out to have no matches, so that's wasted effort there. So how many pages do we have to read in order to answer the query? Right, first thing we need to work out, how many pages of tuple descriptors do we need to read? And then, given that, that's going to indicate a set of pages. Some of them contain true matches, some of them don't. So let's see. Ooh, that's not.
You think that 90% and 10%, is there any reason to think that would generally be the case, or is that just...
No, that's just assumptions that I've pulled out of the air. So it might be worse, it might be better, who knows. Why did I pick 9 and 10? It didn't sound too bad.
I mean, is there a general tendency that false matches would occur on pages with true matches?
No. There's absolutely no reason why they would. Okay. So I'm just assuming that most of the time when we have a false match that happens to occur on a page with a true match. If it was 50-50, then sure, we're wasting a lot more page reads than we need to. Given the false match problem, I guess this has nothing to do with these values. So yeah, you're right. So that's not what I wanted. What I wanted was this. No, I wanted these. Right. So I think I've worked it all out here. So that's the yeah. Right. So how many data pages? That was easy. The numbers were engineered to make it easy to work out. 1,024. How many pages of signature data? Now this is interesting because that's a fixed overhead that we have to read every time we answer a query. So how many signatures per page, which is basically what that's going to give us. So we can fit 1,024 signatures per page because each signature is 8 bytes long, and we've got 8K in a page. How many signature pages are there then going to be? Remembering that there's one signature for each of those tuples, so 100 pages of signature data. All right, so the true matching pages, I think I said in the outset that was 100. So the real matches are located on 100 pages. So how many false matching records are we likely to have? And I've got, once again, about 100 false matching records. Now, 90 of those also occur on pages with matching tuples. 10 of them occur on pages by themselves. So the 90 of them don't have an effect. Now, of course, if it was 50-50, then this number here would be 50, which is significantly more than 10. All right, so total number of pages we have to read. We have to read all the signature pages. That's those ones. We have to read the pages that contain matching tuples. And by the way, we're never going to miss a tuple. You kind of get the feeling that maybe that's possible, but it's not under this scheme. So we'll always find the tuples that we want, plus we're going to find some annoying extra ones. So that's the total number of pages that we have to read. Like I said, if this ratio here was more like 50-50, then we still have to read 100 pages, and then we'd have to read 50, so we'd read 40 more pages. So 210 pages. How does that compare to hashing, or how does it compare to multi-attribute hashing? In some of the scenarios with multi-attribute hashing, when we had a lot of stars, we'd have to read a lot of pages, so potentially okay. If we had a really good hash function and we were doing a query on the hash key, then maybe only one bucket, so that would clearly be a lot better. If we got a B tree, for example, that's probably it's clearly going to be a lot smaller than that as well. So all we got to do is traverse one branch of the B tree, likely to be maximum 3 B tree nodes, and then that'll take us to the page containing the matching tuple. If it's not a primary key, then we may have to read more of the data file. Alright, so that was one descriptor per tuple. Potentially that's a lot of descriptors we have to read, especially if we've got 100,000 tuples. Say, even if we stack a lot of them on each page, it's still quite a few pages we have to read. So we saw the 100 pages of signatures that we had to read in the previous example. what happens if we try to do one descriptor for each page? So effectively what we're going to end up doing is treating the page like a giant tuple, taking all of the attribute values and forming a big code word. It's obviously going to be larger than a code word for an individual tuple, but a single code word for the whole page. So if we got something like this, 4 attributes, 128, where's that C coming from? 128 tuples per page, okay? And that's the false match probability. Now it's 1 in 1,000. Then we're going to end up with a signature for the page, which is 7,000 bits. That might sound a lot, but when you turn it into bytes, it's only 900 bytes. We can stack a few of those into an 8K page. We can stack 8 of them, in fact. So that many page descriptors. So now, remember that what we were doing before when we read individual tuple signatures, where ultimately we worked out that they corresponded to a page, and we have to read lots of tuple signatures, and we may end up hitting the same page multiple times. Here what we're doing is we're simply reading page descriptors, so now we don't have to read a tuple for a signature for each tuple, we read it for each page. Of course, it's a larger signature. So the scan is, here's the page descriptor for page 0. If the query descriptor and the matching test is the same as what we had before. We form a query descriptor which is this large, and we check whether the bits in the query descriptor are a subset of the bits in the page descriptor, and if they are, then potentially that page contains matching tuples. So we read through this, and that'll give us a set of pages that we need to go and read. Right, so what does that cost, and are we going to save anything? So similar kind of setup to what we had before, except now we're doing page level descriptors. So what's that going to cost? Right, so this is the setup, number of data pages, same as before. Number of signatures per page, now it's a lot less than it was before. And I think I wrote a little program to work out the M and K, so I didn't even write down what M was. In any case, we can kind of work it out. It's that's 512 bytes, so multiply 512 by 8, so it looks like 4K bits in each of these page descriptors. So we can fit 16 of them on a page. We'd have 64 signature pages, which is a little bit less than what we had for the individual tuple descriptors, tuple signatures. Alright, so how many pages do we have to read? Once again, we assume that the data file is exactly the same as it was before. It's just we've got a different signature setup. So we read 64 signature pages. 100 data pages contain matching tuples, so that's fine, that's not going to change. And we end up with only one false match page. So we've read less signature data, and we end up with less false matches, and thus we end up with relatively small. I'm wondering why that isn't 10. should be the same as the previous one. Let's assume that I messed up the arithmetic somewhere up here, and because the false match probability is the same, so we're likely to end up with the same number of false match pages. So anyway, that will be 175, which is less than what we had before. So we saved a little bit. Now, can we do better using this kind of strategy? And it turns out that we can, if rather than having one descriptor per page, which is length m, we switch the descriptors and kind of take them vertically through the signature file. So what we have here is B descriptors which are length B, where B is the number of data pages. Okay. So if we read these slices vertically, then we're going to get the same page descriptors as we had before. Okay. But so rather than having B descriptors, each of which is m bits long, we have m descriptors, each of which is b bits long. Okay. So how does that help? Well, one trick that we can use, previously when we had the query descriptor, we'd have to compare it against each page descriptor. So we'd have a query descriptor that was length m, we'd do the subset check on that, then we'd do the subset check on that, then we'd do the subset check on that, and we'd have to do that for all B pages. If we slice it, and what we're really interested in there ultimately is working out if I should have put a copy of the query descriptor somewhere here, but what we're really interested in is finding pages that have a bit there, a bit there, a bit there. So we're only interested in some bits, the bits that correspond to the query descriptor. So if we arrange the signatures like this, then we can look at the query descriptor and we can simply grab all of the 1 bits, and they're the only bit slices that are interesting to us. So we got a 1 here, so we look at that bit slice, and we've got a 1 here, so we look at that bit slice, and all we have to do is AND all those bit slices together, and it's what's left is going to be a list of, it's going to be a sequence of B bits, but the 1 bits are the bits that correspond to pages that potentially contain matching tuples. Okay, so if we have relatively small number of bits set in the query descriptor, we only need to read a relatively small number of bit slices. Okay, AND them together, that gives us a B bit string. Each 1 bit corresponds to a page that that potentially contains matching tuples. And so this is the way you actually do it. So initially so this matches thing is a B bit long bit string. Initially we set it to all 1s, assuming that maybe all pages contain potentially matching tuples. And then we look at we look through the query descriptor, and we only look for the 1 bits, and we work out the index of the 1 bit, and then we look at the corresponding bit slice and AND it in with the matches. So if it's got a 0 in the bit slice, it means there can't possibly be tuples in that matching tuples in that page. So after we've done all of these, we end up with a value for matches which has 1 only in the bit positions that correspond to pages that may contain matching tuples. So that's what this is doing down here. It's searching for all the 1s, and it's reading those pages and then scanning for matching records. So this is useful because it basically means we're going to read half the number or half the amount of data. Now that's not strictly true. We're certainly reading half the amount of bits, or we're manipulating half the amount of bits, but the bit slices are contained on pages, of course, so we have to read some number of bit slice pages. So we can analyse the cost here. Let's have a look, which I've done. Alright, so let's see. Alright, so the number, so B is the total number of pages, data pages, and so the number of bytes corresponding to that number turns out to be 128 because there are 1,024 data pages. So each of our bit slices is 128 bytes long. So that's the number of bit slices we can fit on each page of the signature file, and that's the number of pages in the signature file. Although, where did the 4,000, right, yeah, that's right, because there are 4,096 slices. Okay. So 64 pages where each page contains 64 slices. So we need to read 10 slices, and in the worst case, so here we're assuming, so we're forming a query signature, it's got 10 bits set. Okay. If it's only got one attribute, that's kind of likely. In the worst case, these 10 slices all happen to be on different pages, so we'd have to read 10 pages of bit slice data. If we're lucky, they might be on half that many pages, because some slices or multiple slices occur on a single page. Alright, so if we work through the thing, and once again I have a feeling that should be 10 rather than 1, then that would be 121. So now we're down to a little bit less amount of data to read. So whatever happened, however we had to do this, we'd have to read 100 pages of data, because the matching tuples are on 100 different pages. Right? So the overhead that we're getting from the signature matching is about 21 pages, which is kind of plausible. So this approach can lead to reasonable performance. So remember that the whole point of this was that we abandoned, log or order one cost functions. We're simply doing effectively a linear scan of the signatures to try and work out where the matching tuples might be. So even with that, the way we've structured the signature data, we've ended up with overhead like that. Let me see. So that would be true, say, if we only had one attribute set in the query. If we had more than one attribute set, we might have twice as many bits set, so therefore we need to read twice as many pages. So that's an approach that would allow us to do a bit of filtering as well. And like I said earlier, the way that's structured, it doesn't at all limit us to the location of the tuples. So we could easily have a sorted file, we could have an index on it, as well as having this signature file. So potentially we could use the signatures in conjunction with something else. Alright, that'll do for the first hour, and I'll talk about